Hello everyone, welcome to this next lecture in building neural networks from scratch. Before we move further to activation functions such as softmax, etc., I want to cover two aspects of coding in Python. The first is array summation, and the second is broadcasting rules in Python. I have seen that a number of students are really unclear about these two topics in Python coding, and they show up at a number of places, not just in neural networks, but several other aspects of machine learning as well. And they can be a bit complex to understand. But once you understand the basics, then you will never forget these concepts. So I think it's worthwhile to have a separate lecture on these two concepts. If you are already aware of these, then please feel free to skip this lecture and directly move to the next one. So I'm going to zoom in a bit on the array summation right now, and then we will move to broadcasting in the second half of this lecture. Okay, so let's say we have an array as is given here A, which has three rows and three columns, and I'm going to show you different summation commands in Python and the differences between them. First of all, if you just use np, which is numpy.sum of array A, what it will do is that it will just sum up the different elements of this array: 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, and the resulting answer will be 45. So that's the simplest way to sum this array. However, when you do the summation, there is usually a second argument which is called axis. And this is quite important because sometimes we just want to sum the rows of this array, sometimes we just want to sum the columns of this array. So let's say if you write the same command np.sum a comma axis equal to none. If you say axis equal to none, what will happen is that it will just do the same thing what it did in the summation operation we saw earlier. It will just sum up the different elements and we will again get an answer of 45. The real difference starts to come when we use the axis values as 0 and the axis values as 1. So this might be a bit confusing to remember. So just keep in mind that if we write this command in p.sum a comma axis equal to 0, it just means sum the rows of the array. That's it. And when we write this command np.sum a comma axis equal to 1, it means sum the columns of the array. So for example, let's look at this command np.sum a comma axis equal to 0, which means we have to sum the rows. And the first row of this is 1, 2, 3. The second row is 4, 5, 6. And the third row is 7, 8, 9. And we will be summing the rows. So 1, 2, 3 plus 4, 5, 6 plus 7, 8, 9. So the answer here would be um, the first row plus the second row plus the third row. And the answer would be 12, 15, and 18. In the second case, if we do np.sum a comma axis equal to 1, it means that we have to sum the columns. So it will take the first column 1, 4, 7, take the second column 2, 5, 8, and take the third column 3, 6, 9, and add them together. So if you add these together, the first element would be 6, the second element would be 15, and the third element would be 24. So this is the answer in this case. In both of these cases, if we don't specify anything after the axis, like a third argument, if we say axis equal to 0 or axis equal to 1, the resulting answer is an array with one dimension. So this is not a two-dimensional array, it will just be one. So if you plot the dimensions of this in Python, you will get just 3. If you plot the dimensions of this in Python, you will just get 3. You won't get 3 by 1 because it's not a two-dimensional array, it is a one-dimensional array. And although this might sound like a minor detail right now, it is very important to keep in mind. Now, if let's say we want the summation along the row and summation of the column to be a two-dimensional array, so if we want this to be 3 by 1 and this to be also 3 by 1, then there is another argument which can be used, and that is called keep dims. This is actually keep dimensions, but the shorthand notation in Python is keep dims. And the thing is, if we use keep dims equal to true, what it will do is that it will represent that sum as a two-dimensional array. So let's say if we do np.sum a comma x is equal to 0, it will sum the rows, but the resulting answer will be a two-dimensional array. So if we sum the rows here, the resulting answer will be 12, 15 and 18, but the dimensions of this will be 1 by 3. So that's what it means when keep the dimensions. So A was a two-dimensional array, right? And when we do the summation, we are telling that I want to keep the final answer also as two dimensions. That's why it's called as keep dims equal to true. This will be very important when we learn about the softmax activation. So keep this in mind. Similarly, when we do np.sum a comma x is equal to 1 comma keep dims equal to true, it will sum the columns. So column 1 plus column 2 plus column 3, and the result will be a column vector, which is a 3 by 1 vector, and also it will be a two dimensional array. So remember that when you use keep dims equal to true and x is equal to 0, the resultant will be a row vector 1 by 3. And if you do x is equal to 1 and keep dims equal to true, the resultant will be a column vector which will be 3 by 1. Okay, this is the np.sum in Python. So it's not as simple as just passing in the array. There are two additional arguments which we learnt about. The first argument is called axis, and the second argument is called keep dims, and both of them are very important if we want to sum along rows and if we want to sum along columns. Now let us look at the second main section of this lecture, and that is broadcasting rules. So you might have noticed earlier that when we did np dot x comma w transpose plus b, this is a bit weird, right? Because if you do this, this is a 3 by 3 matrix. So let's say it's 1 1 2 1 2 3 and 3 3 1. But this is a 3 by 1 matrix, so it might be 1 comma 2 comma 3. And you might be thinking that how can we add these two? This is a 3 by 3 and this is a 3 by 1. How can we add these two? So it is possible to do such additions or even such multiplications, subtractions, divisions in Python if you understand what is called as broadcasting rules. And different libraries have their broadcasting rules, such as if you type numpy broadcasting, you'll be taken to this document. If you type pytorch broadcasting, pytorch is also a library for neural network coding, then you will see this particular documentation. I'm going to tell you very simple rules about understanding broadcasting, because if you read this, right, it might be difficult to understand. So here it says two tensors are broadcastable if each tensor has at least one dimension, and when iterating over the dimension sizes starting at the trailing dimension, the dimension sizes must either be equal, one of them is 1 or one of them does not exist. Pretty difficult to understand this, and you have to take some examples on paper to really understand this. So let us look at broadcasting rules. Okay, so usually these rules are: you scan the dimensions from left. The arrays are broadcastable if the dimensions when scanned from left are either equal, one of them must be 1, or one of them does not exist. So either the dimensions must be equal, one of them must be 1, or one of them does not exist. Let's see what this means. Let's say I have a matrix which looks like this. It's a 3 by 3 matrix: 1 2 3 4 5 6 7 8 9. And I have the b matrix which looks like this: 1 2 3. So it's a 3 by 1 matrix. Let us see if these two matrices are broadcastable. So the first rule is that you have to write down these dimensions. Okay, write down the dimensions so that they are aligned. So let us write it down. 3 by 3 is the dimensions of the first matrix, and 3 by 1 is the dimensions of the second matrix. Okay, now we have to start scanning from left to right for every single dimension. and the arrays are broadcastable only when the dimensions are equal, one of them is 1 or one of them does not exist. So let's start scanning from left to right. First we encounter this first dimension of both the arrays, and one of them is equal to 1, so that is satisfied, so I'll write a tick mark here. Then we move to the second dimension, and here we can see that both dimensions are equal, so it satisfies. So both the dimensions here have satisfied that either they must be equal, one of them must be 1 or one of them does not exist. So these two arrays are broadcastable. So what does it mean? It means that when we do an operation such as a plus b, what Python does internally is that it copies uh, b three times so that the shape of b matches the shape of a. So let's say if you have a plus b, and a is 1 2 3 4 5 6 7 8 9, and plus if b is 1 2 3. So the way Python does this summation is that it says that no problem, I'll just uh, copy the dimensions of b, or I'll just expand b further by replicating its values so that size of b matches the size of a, and then you can do this summation operation, right? Like you would always do, add 1 and 1, 2 and 1, etc. Now you can do this summation. This is exactly what is done over here. When we do np.x comma w transpose, although this matrix is 3 by 3 and 3 by 1, they are broadcastable. So what Python does is that it converts the B matrix to 1 2 3 1 2 3 and 1 2 3. It copies it so that the size of B satisfies the size of this dot product. And this is exactly what is written in the NumPy documentation. So if you were to add a matrix or an array like A, which has three elements with B, Python stretches or copies the values of B two times till these two shapes match each other, and then it does the addition. So this is what is meant by broadcasting rules. Okay. Now I want to take one more case. So we looked at A plus B, right? But what if B is like this? 1, 2, 3. So what if B is this? Or let me call it C. This is one row and three columns. Again, first let us check whether A and C are broadcastable. So let us write these dimensions so that they are aligned. We have written this down. Now let's begin scanning from left to right. So the first set of dimensions are equal, so they satisfy. And in the second set of dimensions, one of the dimensions is 1. So that is also satisfied. So then these two are broadcastable. So what Python will do is that it will create copy. So it will extend this to 1 2 3 and 1 2 3, and then it will add these two or multiply these two. But remember the way uh, B is extended and the way C is extended is different. B was extended column wise and C was extended row wise because that's their original shape. So the way Python extends these matrices is by maintaining their original shape. That is very important to keep in mind. Now let us take a very interesting example in which we are looking at two matrices. One is a two-dimensional array and one is a one-dimensional array. And let us see whether they are broadcastable or not. This will again directly related to the keep dimensions. So remember, if we don't use keep dimensions, we get an array with one dimension, right? Let us see how the broadcasting works with these two. So A is a two-dimensional array 3 by 1 and B is a one-dimensional array. So let us see if they are broadcastable. What the broadcastable rule says is that first we have to write down the dimensions so that they are aligned. So 3 by 3 is the dimensions of A. And for B, now the thing is it has only one dimension, which is 3, and it's not does not have the second dimension. So we begin aligning it. So first we write 3 and then there is nothing here. Nothing. Since it is not a two dimensional array, right? It's only one dimension. So these are the dimensions of B. Now let us start testing whether they are broadcastable. So we'll start scanning from left to right. So let's look at the first set of dimensions. They are equal. So this is fine. In the second set of dimensions, notice that one of them does not exist. However, the broadcastable rule also has a provision for this. When we scan from left, the dimensions must be equal, one of them must be 1, or one of them does not exist. So here this dimension does not exist, right? But it's fine since it is mentioned in the broadcastable rule. So great. This will also be done. So which means that these two arrays are broadcastable. So what Python will do is that it will assume that it's a two-dimensional array and replicate this two times. So this B will be reframed by Python as 1, 2, 3, 1, 2, 3, and 1, 2, 3 as a 3 by 3, and it will sum it up. So then this will be the resulting answer. So one more thing to remember is that when there is nothing here, Python replaces the nothing value by 1. So if this has no dimension and if we are still broadcasting, the Python will replace it by 1. So now Python treats B as a 1 by 3, 1 by 3. So then it will just be broadcasting a 3 by 3 with a 1 by 3, which we already saw before. So then it will just copy 1, 2, 3, 1, 2, 3, and 1, 2, 3 and sum it up. So the reason I'm showing this to you is because I want to take two examples here and show you, if you're not careful, how knowledge of these two things can help you, or if you are not knowledgeable about the keep dims and the broadcasting rules, how it can land you in trouble. So let's say we have the matrix A, and I give you the task that from each row of A, you have to subtract the maximum value of that row. So basically what it means is that from first row, you have to subtract the value 3. From the second row, you have to subtract the value 6. And from third row, from each entry, you have to subtract the value 9. Which means that from the first row, you have to subtract 3. So 1 minus 3. First entry will be minus 2. Second entry will be minus 1. And third entry will be 0 of the first row. From the second row, you have to subtract 6 from all entries. So first entry will be minus 2, second entry will be minus 1, and third entry will be 0. And for third row, you have to subtract 9 from all the entries. So again, it will be minus 2, minus 1, and 0. So this is the answer which we expect. Okay. Now let us see how you can do this in Python. So the first thing is that I have to take the maximum along each row, right? So I will use np.max a comma x is equal to 1. What x is equal to 1 does is that, remember that it will just do the calculation along the column. So what it will do is that it will first take the maximum along this row. So it will take a look at these three columns and take a maximum. So then that will be 3. Then it will take a look along. So remember, x is equal to 1 deals with columns, right? So it will look at the first column, the second column, and third column, and then take a maximum of these three for the first row. So then that will be 3. Then it will look at the second. So then that will be 6, and then that will be, and then it will look at the third. So then that will be 9. Correct? In the second case, what we do is we do np.max a comma x is equal to 1, but we do keep dims equal to true. So what this will do is, again, this will result in a maximum values from each row, 3, 6, and 9, but it the resulting dimensions will be 3 by 1, and the resulting dimensions of this will be one dimensional array. Now if you do a minus this, remember the broadcasting which we saw, this is a is 3 by 3, and this let's say call this b. This will be something like nothing dimension here and 3 here. So what we saw exactly in broadcasting is that the Python fills the nothing dimension with 1. So then this will be treated like a 1 by 3. So then what we will do here is that this will be replicated 3 times, 369, 369, 369. So the resultant would be that from the first row, different values are subtracted. We need 333 to be subtracted from the first row. So we will get a wrong answer here. Whereas if you look at the second case, it will be a, which is 3 by 3, minus a 3 by 1. So the Python will replicate this column wise. Since because keep dims equal to true, we retain this as a column vector. Remember, when we use x is equal to 1, we retain a column vector, right? Similarly, here what has been done is that we have retained a column vector here. So this is 3 by 1. So while broadcasting, this column will be replicated 369, 369, 369. So from the first row, from all values 3 will be subtracted. From the second row, from all values 6 will be subtracted. And from the third row, from all values 9 will be subtracted. So it will lead us to this, which is exactly what we expected here. So this leads to the correct answer. But if we do not use keep dims equal to true, it leads to the wrong answer. That's the importance of understanding the keep dims function and the broadcasting rules in Python. Remember, at the x is equal to 0 and the x is equal to 1, which we learned for np.sum, that works for any function. What we did was np.max a comma x is equal to 1, which means that it will take the maximum value by comparing the columns. So it will compare the first column with the second column, third column, and then it will take the maximum value. So then the resultant will be 3, 6, and 9. Because if you compare the first column with the second column with the third column, the first value will be 3, second will be 6, and third will be 9. uh, okay, and the reason we failed here is because we did not use keep dims equal to true. So while broadcasting, Python treated it as a 1 by 3 array, and that was replicated 3 times, 369, 369, 369. So from the first row we ended up subtracting 3 from the first element, which is 1. We ended up subtracting 6 from the second element, which is true 2, and we ended up subtracting 9 from the third element, which is 3. So it led to completely wrong answers, whereas keep dims equal to true led to the correct answer. And I have implemented the code for this in Python. So here you can do np.sum, and it will do 45. But if you print np.sum a comma x is equal to 0, it will sum along the rows. So we will get an answer of 12, 15, and 18, which is what we have got here. And if you print the shape, as I mentioned, it will be a one dimensional shape since you are not using keep dims equal to true. So it will be just 3 because it's a one dimensional array. When we do np.sum along x is equal to 1, it will lead to the answer 6, 5, 14 since we sum the columns. So 6, 5, 24, sorry. And if we print the shape, it will again be a one dimensional array with 3 elements. Now let us look at keep dims equal to true. So if we sum along x is equal to 0 and keep dims equal to true, the answer will be 12, 15, 18, which is the same as when we not kept keep dims equal to true. But look at the shape. The shape is 1 by 3, which is a 3-dimensional row vector. Sorry, 2-dimensional row vector, exactly like we saw over here. And then when we kept keep dims equal to true and we summed along x is equal to 1, the resultant is 6, 5, 24, which is exactly the same as the result here, but now it's a column vector and a two-dimensional array of 3 by 1. So just keep this in mind, and we can actually try one more thing. We can also do print np dot max a comma x is equal to 0, and we can print np dot max a comma x is equal to 1. Okay, so if you print along x is equal to 0, and if you take the maximum values, it will compare the rows. So the answer will be 7, 8, and 9, which is this 7, 8, and 9. But like what we have done over here, if you do np dot max along the axis, it will along x is equal to 1, it will compare the columns. So then first column, second column, third column. So the answer will be 3, 6, and 9, which is exactly what we see over here. So I'll be providing these codes also with you. I'll be sharing these codes on the information section. So please try to run this. The reason I'm going into these many details is that if you understand the array summation and the broadcasting rules, you will not get into difficult situations when we deal with softmax or other functions later, and debugging will also be easier to you. So thank you so much everyone, and I look forward to seeing you in the next lecture.